Nice. So yeah, welcome everyone to another week's Intercontinental seminar on gravity and cosmology. This week we have the pleasure to have with us Sourav Bhattacharya. Sourav got his PhD in Kolkata, I think, in early 2010s, and then I had the pleasure and the opportunity to meet him in Crete while I was doing my master's. He was a postdoc in Crete with Theodore Tomaras. And after that, he moved back to India, to Pune, and then IIT Ropar, and now he's in Jadavpur, Kolkata. And today he's going to talk about psi r phi square non-minimal coupling and the leading order long-range perturbative quantum gravity effects. Yeah, the floor is yours. Thank you very much.
Okay, good afternoon and thank you very much. I thank Konstantinos for giving me this opportunity to present here. So, as he said, today I'll be talking about psi r phi square non-minimal coupling and the leading order long-range perturbative quantum gravity effects. So, this is some direction that proving this perturbative quantum gravity effects that I have started along with two of my PhD students, Mr. Abhijit Sen Mujumdar and Mr. Owen Noskor, here at Jadavpur University. So, okay, so let's begin. So, all of us are familiar with four fundamental interactions of nature, and these are strong interactions, weak electromagnetic, and gravitational interactions. We know that first three of these four interactions can be quantized, and we can do quantum field theory with these interactions, and we can predict things, we can calculate things, and we can predict things like scattering amplitudes, decay rates, and I mean various other corrections to classically measured quantities, and these are in excellent agreement with observation. However, if one tries, this is well known that traditionally to quantize general theory of relativity or any other alternative theory of gravity or existing alternative theories of gravity, they turn out to be non-renormalizable. Now, what is renormalizability? I mean, whenever we do quantum field theory, there are certain processes in perturbative expansions where one needs to sum over or integrate over the momenta of the virtual particles. Virtual particles always appear in quantum processes as internal particles which cannot be seen, but often we need to integrate their momentum. And they often give rise to divergences, and these divergences are usually cancelled by uh, modifying the coupling parameters or certain parameters of the theory, like the mass, like the coupling constant, like the field strength, etc. However, the general relativity or gravity, I mean, whenever we try to quantize it and try to renormalize it, it turns out that at each order of expansion of the inverse metric of general relativity with respect to some fixed classical background, we go on producing new kind of interaction terms, and these interaction terms actually need new kind of counter terms, so requiring effectively infinite number of counter terms at each order of the counter terms, and that's why we say that this theory is not renormalizable. A renormalizable theory is such that we can absorb all the divergences to all loop orders, to all orders of perturbation theory into some finite number of counter terms only, not into infinite number of counter terms. So this is a very well-known feature of general relativity, and this has been clear since the 1970s through the pioneering works of, I mean, many people like Boulevard, Deser, Weltman, Weinberg, 't Hooft, and so on. Now, the fact that gravity is not a renormalizable quantum field theory has led to many alternative ideas for a consistent theory, to achieve a consistent theory of quantum gravity. For example, string theory, loop quantum gravity, emergent gravity, causal set theory, and so on. However, it will be fair enough to admit that none of this theory has so far given us any complete or satisfactory answer about quantum theory of gravity. We still yet do not know what is a complete picture of quantum gravity. Now, despite this incompleteness, it is believed that at energy scales much below that of the Planck's mass, at least the first couple of orders of computations in the standard perturbative framework might be perturbative quantum gravity framework I mentioned, which is not renormalizable, might be physically meaningful. The predictions thus made can be hoped to be tested in the not too far away future, hopefully, well, because we can be hopeful about this because the observational capability of us are increasing day by day, especially keeping in mind the improving observational capacity to probe the strong gravity regime, for example, near a black hole event horizon. They can tell us also whether the notion of graviton as the quantum of gravity makes any sense at all or not. One hopes that these low energy predictions will one day be successfully embedded into a complete quantum theory of gravitation. So, perturbative quantum gravity framework, as I said, is known. I mean, the framework is known since 1970s, and it was accepted that it is not renormalizable, so it's a shortcoming. And then Donoghue and his collaborators actually once again advocated this framework with this motivation that well, let us do some computations, let us predict some results, and let's see what happens. So this is a very humble approach, humble proposition, because it doesn't claim that it solves the problem of quantum gravity, but yet it can be physically very well motivated. At least I find this is physically very well motivated because it can make some predictions which can be tested, maybe not now, but maybe in the future. So with this motivation, the community has been endeavoring to understand various predictions of perturbating quantum gravity. They chiefly involve quantum corrections of the long-range two-body gravitational potentials, renormalization of matter-graviton interaction processes like the self-energy, like the vertex functions, and running of various couplings, for example, running of the Newton's constant or any matter coupling. Quantum corrections to long-range gravitational potential may lead to terms breaking the equivalence principle. Quantum corrections of gravitational light bending has also been attempted recently. Quantum gravity computations are also relevant in the primordial inflationary background. I mean, the calculations I have been mentioning here, for example, the potential or the bending of light are essentially done in the weak gravity regime, where the background metric can be taken to be flat, right, the Minkowski. However, they can be also very relevant in the context of the early primordial inflationary background, where the space-time background is not flat, but instead they are taken to be de Sitter or some variant of de Sitter. In this context, the loop corrections due to gravitons can also be physically very well motivated because they can affect the cosmological correlation functions, which are the observables in cosmology. Now imagine, a quantum scalar field theory with a quartic self-interaction, lambda 5/4 quantum field theory with the standard canonical, kinetic term and quadratic kinetic term plus the mass term. This is perfectly renormalizable in flat spacetime in 4 spacetime dimensions. However, if we turn on the gravity, we take a curved background or turn on the gravity, it turns out that this theory is not renormalizable unless we add to the action a matter-gravity non-minimal interaction in the form xi r phi square, half xi r phi square. Xi can be anything. Xi just is a dimensionless coupling. It can take any values in principle. Thus we can. It is evident from this renormalizability argument that I'm talking about the renormalizability of the scalar field. Okay, I'm not talking about the renormalizability of gravity here. So, it turns out then the non-minimal interaction is natural in the presence of gravity in the context of the scalar field theory. In particular, let us recall that for xi equals 1 by 6 and for a massless scalar field, we have a conformally invariant scalar field theory, and it leads to trace or conformal anomaly. I mean, conformally invariant field theories do not have any scale, any energy or mass scale. However, I mean, whenever we take a curved background and take quantum effects, actually the curvature introduces a length scale or mass scale, and that breaks the conformal invariance, and that is called conformal anomaly. So it is a very old result. And also black hole solutions with conformal scalar field theory with or without a cosmological constant is also very well known. Now let us look into the quantum gravity, look this issue from the quantum gravity point of view. Let us we'll essentially work in the weak gravity regime, so that we'll take the metric to be nearly flat. That is, there is a flat background, eta mu nu, the standard Minkowski background, and a perturbation over it. This kappa is the coupling in this quantum gravity, perturbative quantum gravity calculations, with kappa square equals 32 pi g. Usual or minimal matter gravity coupling is generated from this, Lagrangian term, Lagrangian density term, which is square root of minus determinant of metric, and then this curly L is the Lagrangian. Pi stands collectively for any matter field we have. And actually, if I now expand the metric G mu nu in terms of this decomposition into background and fluctuation, then we actually generate interactions between this H mu nu and the matter field, and the standard minimal matter gravity interaction produces vertices like kappa H mu nu T mu nu. T mu nu is the energy momentum tensor of the matter field phi. Now we all know that T mu nu contains derivative of the matter fields. Now this vertex, then, since there is a derivative of the matter field, when we quantize the field, it will contain explicitly momentum of these matter fields. It will be more clear technically when although it may be already familiar. However, so let us instead, if we consider now this non-minimal interaction, this g r phi square term, and we now expand this root g square root and r term in terms of this decomposition, it is clear that it will generate, actually, this is an infinite series of H mu nu. So it will generate two scalar and n graviton vertices. However, the fundamental difference of this non-minimal interaction term with this usual minimal one, that here I do not have any derivative of the scalar field phi, and hence I do not have any explicit appearance of the scalar field's momentum in the corresponding vertices. See, in this minimal vertex, hello, can you hear me, Kostas?
Yes, all good. Yeah.
Okay. So I thought I got disconnected. Okay, fine.
Yeah.
So in this minimal vertex, H mu nu contains no derivative, so no explicit appearance of the graviton momentum. In the non-minimal vertex, this R, the Ricci scalar, will contain derivative of the metric, and hence it will contain explicitly the momentum of the graviton. This one, the minimal one, contains explicitly the momentum of the matter field. The non-minimal one does not contain explicitly any momentum of the scalar field. So this is, they somehow complement each other, and they are qualitatively different. So so that's why, despite these qualitative differences, the xi vertex, this I'll call this non-minimal vertex or xi vertex, remains largely less explored in the perturbative quantum gravity literature. So in this talk, I wish to discuss the effect of xi on the long-range two-body gravitational potential at the leading order via the 2 to 2 scattering amplitudes with graviton exchanges. Gravitons will be here virtual particles. They are not visible from outside, but they mediate the gravitational force. For various massive spin fields, inclusion of a positive cosmological constant will be mentioned very briefly. Also, some results of the effect on xi on bending of light will be shown, Very briefly, once again, finally I conclude with some possible future directions. And in these computations, we'll take xi to be small so that we can make perturbative, we can treat this term xi square root of minus g r phi square perturbative. So let us begin. Here is some algebra. So let us consider first scalar scattering. So what is its application in gravitational scenario? So you see, let us imagine that there is sun and there is a planet, let's say Mercury. Okay, so effectively we can we can model the sun as some scalar here, whatever, that's what we are doing, and Mercury as also a scalar, and we want to find out using quantum scattering techniques that what should be the gravitational interactions between them, gravitational potential between them in the presence of a minimal interactions. So this is the action. So there are two scalars here. We'll investigate the scattering between two scalars. So both scalars, their masses are different. We have kept the non-minimal interaction term xi to be the same for both cases. However, we can we can take different non-minimal coupling parameters. Let's say xi1 and xi2. But for simplicity, I'll keep them same. But calculations with different xi values are easy, straightforward. So the metric perturbations are like this, that g mu nu is eta plus kappa h mu nu. However, when we invert this metric, it acts like an infinite binomial series, and it goes like this. And that creates the main problem. That is the culprit term. Whenever we want to do this perturbative quantum gravity calculations, there are infinite number of terms here in this series. And as well as the square root of determinant g, there are infinite number of terms. The Christoffel connections accordingly, since it contains inverse of the metric in front of it, it also contains infinite number of terms. So this kappa will serve as the expansion parameter. Sorry. So h means the trace of this h mu nu taken with respect to the flat metric. In D. Donder's gauge, so this is a gauge fixing condition because this h mu nu is a constrained field, so we need to get rid of the spurious degrees of freedom. So we fix some gauge, and we obtain accordingly the free graviton propagator is given by this delta mu nu alpha beta. Mu nu is a pair of index standing for one piece of graviton field like h mu nu, alpha beta another h alpha beta. So this gives us the propagation amplitude. So, and this tensor P curly P mu nu alpha beta is given by this. The scalar field's free propagator is given by this. So the two scalar one graviton and the two scalar two graviton minimal vertices, as I said, that I have this action here, and when I decompose this, substitute this G inverse mu here, and I also expand this square root of determinant minus g, I generate interactions between the scalar field and this graviton field h mu nu. So we generate accordingly vertices. These are the standard minimal vertices. This is the two scalar one graviton vertex, and this is the two scalar two graviton vertex. And also we note that from this action, this xi r phi square term, the first and second order non-minimal terms read like this. First one is phi square del square h mu nu, and other one phi square is omnipresent in all orders. Only the graviton terms change, and I have this. So these vertices look like this. Sorry again. The vertices look like this. So I'll denote this non-minimal vertex by a dark circle putting on the vertex. If there is no dark circle here, it will represent minimal vertex. So the non-minimal vertex, the minimal vertices also would look like this. This the first two. Only thing is that according to our notation, this dark circle will be absent for both cases. Now, for these non-minimal vertices, when these interactions, if we wish to calculate the non-minimal vertex functions in terms of the momentas, are reads like this. The first one is this, the second one is this. All these momentas, this q square or L1 or L2, they are the momenta carried by the graviton field and not by the scalar in the non-minimal vertex. On the other hand, for the minimal vertex, these k and k prime momenta are carried by the scalar field, as I pointed out earlier. Now, K1 and K2 and K1 prime and K2 prime are respectively the incoming and outgoing momenta. For example, let's say the scalar 1, which has K1 and K1 prime momentum, and K2 and K2 prime for the other scalar. So I have this momentum conservation, and the transfer momentum, the momentum transferred from one particle to other particle, is denoted by Q, which is Q equals K1 minus K1 prime equals K2 prime minus K2. We'll take K1 or K1 prime, K or K prime to be non-relativistic. It's a very reasonable approximation. Let's say we are talking about the gravitational interactions between two static masses. Let's say Sun and Mercury, their speeds are not comparable to the speed of light. So that's what we'll do. So this is the lowest order, Feynman diagram for this, or tree-level Feynman diagram for this scattering amplitude. If I use this one is the non-minimal vertex. Either this can be the non-minimal vertex or this can be the non-minimal vertex. For this to be the non-minimal vertex, I substitute these things here, and this is the graviton line. Of course, this scalar comes with momentum k1, gets scattered with k1 prime, this one with k2 and k2 prime. And now this q square stands in the numerator, sits in the numerator due to this non-minimal vertex, and they get cancelled, and I get this scattering amplitude, Feynman amplitude, which is kappa square psi m square. If I have the non-minimal vertex here at this position of little m, this I get little m square replaced by capital M square. However, let's see what happens with the minimal vertex, which is a very well-known result. For the minimal vertex here, this q square doesn't come. Instead, I have this one, right? So accordingly, this q square in the denominator sits. It doesn't get cancelled. And I get something divided by q square. The potential is defined via the Fourier transform of this, Feynman amplitude in the non-relativistic limit. Of course, the potential is always defined in the non-relativistic limit. Relativistically, potential has not much meaning, physical meaning. So it turns out that for the tree diagram, since it does not contain any q, look into this Fourier transform, I have a potential which is delta cube r, which is absolutely local, which is zero everywhere except r equal to 0. It is not a long-range gravitational potential. So at the leading order, that is xi times g, kappa square is g. For non-minimal vertex, I do not have any long-range contribution. For the minimal vertex, however, I have a 1 by q square here in the Fourier transform, and 1 by q square Fourier transform is 1 over r, and accordingly I get reproduce Newton's law. So we can see the difference now. Now, so let us go to the next to the leading order. The next to the leading order is order xi g square. There are series of diagrams, in this, and due to this non-minimal vertex, due to the placement of the non-minimal vertex, I have various sub-diagrams. For example, this diagram is known as ladder diagram, and the second one is called the cross ladder diagram. And here, you see this is the non-minimal vertex in this K1 line, and I can place this non-minimal vertex on the K1 prime or K2 prime or K2 vertex, K2 line. So I have 4 subcategories in this ladder. Likewise, I have 4 subcategories for the cross ladder as well. So for this category, this subcategory, for the ladder, I get this amplitude, and we find, see, I want to find out long-range gravitational potentials, which essentially is non-analytic in R. That is, it should behave like 1 by R, 1 by R square, 1 by R cube, like this. So in order to have that, I must have contributions which are non-analytic in Q square, vector Q square. Okay, since I work in the non-relativistic limit, so Q square is basically Q mu is basically vector Q square. So also this diagram does not contribute to the potential, long-range potential in the presence of non-minimal interactions. It's also for the cross ladder, it doesn't contribute. Let us go to the next class of diagrams. These are called triangle group of diagrams. For the triangle group of diagrams also, I mean, the first one, for example, if we take, see, there are 6 subcategories depending upon the placement of this non-minimal vertex denoted by this dark circle. And it turns out that the first triangle diagram does not contribute anything. Likewise, the second and the third and the fourth triangle diagrams. However, the fifth triangle diagrams, I'm sorry, I mean, there is not much end there. So the fifth triangle diagram yields something non-trivial contributions, which contains non-analytic contributions in Q square. For example, the terms containing log Q square, and for example, this Q5. Remember, I'm talking about Q square non-analytic. So any odd power of Q will be non-analytic contribution. So the sixth one's contribution is found by just interchanging the scalar mass m. So I mean, if I now perform the Fourier transform, as I said, I find out this contribution for the two-body potential, long-range potential. So the leading contribution, as you can see, is behaves as 1 by r to the power 4. The next series of diagram is the Seagull class of diagrams. Now here you see that I have a 3 graviton vertex as well. 3 graviton lines are meeting at a point. I have not shown these diagrams, this vertex explicitly, because it is rather lengthy. It is not necessary to show them here. So actually, here also it turns out that the non-trivial contribution for the long-range gravitational potentials comes only for the fifth and the sixth, Seagull diagrams, and they read this. Once again, the leading contribution is 1 over 4 r to the power 4. Also, we have this next. We have this double Seagull group of diagrams. Here you see we need these 2 graviton and 2 scalar vertices. It can be minimal as well as non-minimal. So I take 1 minimal and 1 non-minimal. I restrict myself in linear order in Xi calculations and also order G square, right? I am keeping Xi linear in these calculations because I have assumed that Xi is small. So, both these diagrams actually contribute, and I have these 2 contributions. These contributions are subleading. They behave as 1 by r to the power 5. Next, I have this fish class of diagrams, and I have these contributions, 1 over r to the power 5 subleading contributions. And finally, we have this vacuum polarization diagrams, and they look like this. So note that if I cut this line here and here, that is amputate these two lines, scalar lines, I get graviton self-energy diagrams, one loop graviton self-energy diagrams due to graviton itself. These are 3 graviton vertices, and also I have this one, placement of the non-minimal vertices, and I need to add some contributions from called the ghost contributions, because whenever I have a graviton loop in quantum gravity calculations, since graviton is a gauge field, in order to maintain gauge invariance, we need to add some fictitious particles. These are called ghost or Vati-Popov ghost fields. They actually do not appear in the external lines, so they are not visible, but they are added to the amplitude so that the whole thing becomes gauge invariant and hence a physical quantity. Gauge means, a certain value becomes multiple valued, certain amplitude becomes gauge dependence means multiple valuedness of physical quantities which are not acceptable. Physical quantities must be single valued, right? So this self energy was calculated long back by Tuft and Weltman, and they're given by this. And actually, we substitute it here, this result, and we find this subleading 1 by r to the power 5 contribution. So now, if I put everything together, all these results together, I find this expression for this long range gravitational potential in the presence of non-minimal coupling. So a couple of things to be observed here. For example, you see that there is this, it starts from g square. There is no contribution of g, right, of order g, like the Newton's potential. But as I explained at the very beginning, that there is no such contribution because order g psi contribution gives actually linear terms. Local contributions, which are not long-range gravitational potential. Second thing is that this whole result is symmetric under the interchange of little m and small m. This we expect, right? We have taken both scalar fields to have non-minimal coupling with the same coupling, and of course, if we interchange these two masses, we should get symmetric result. The leading contribution is, as I said, 1 by r to the power 4, and the next to the leading contribution is 1 over r5, and up to 1 by r to the power 8. Okay, so now let us compare this result with the, with that of the xi equal to 0 case. That is a minimal case. For the minimal case, the potential looks like this. Sorry, I forgot to put the references here. It was by Donoghue and his group. And the potential actually, one loop corrected potential looks like this. First one is the Newton potential, and the others are its quantum corrections. And you see that interestingly, the first term, obviously, it obeys the equivalence principle, right? The third term also, this capital M, small m, also obeys the equivalence principle. Particles dynamics. Let's say we want to study little m's dynamics. The accelerations won't depend upon little m for the first and the third term. However, for the second term, it will, and hence it's an equivalence principle breaking term. For the non-minimal case also, the equivalence principle is broken, and it is more severely broken, as you can see. If we wish to study the dynamics of little m in this potential, it will severely depend upon the mass of little m, the acceleration. And also, we note that the absence of any tree-level result, like tree-level potential, like xi g mm over r, actually saves the non-minimal coupling. Because for otherwise, suppose any such potential, we found any such potential, it would actually have killed effectively this non-minimal coupling, just like the Brun's decay parameter from simply the solar system data. So, yes. So now let us take the ratio of the leading part of the non-minimal potential, that is 1 over r to the power 4 term, and with the most subleading or quantum part, this is the quantum part, 1 over r cube behavior of the minimal potential, and let us take capital M to be much greater than m. Okay, so for example, capital M, as I have taken, the ratio reads this. For example, capital M could be the mass of the Earth, and little m could be the mass of the Higgs particle. Okay, and this r, little r, could be the surface of the Earth, radius of the Earth. And here in this ratio, this m is understood as the inverse Compton wavelength of the Higgs particle. So this is really dimensionless, m times r. So, if I substitute the mass of the Earth here, radius of the Earth here, mass of the Higgs is approximately 10 to the power minus 25 kgs. So we can calculate its inverse Compton wavelength, h by n times c. So, I mean, then it becomes, this ratio becomes xi times 10 to the power 6. So remember that, I mean, this term is sitting in the numerator, this non-minimal term. So this shows that maybe, hopefully, if we can probe this, I mean, Newton's law further, I mean, with more accuracy, and we can probe with such accuracy, then we can actually determine that, I mean, whether non-minimal couplings at all exist or not, provided that xi is greater than 10 to the power minus 26. So we expect xi to be small, but 10 to the power minus 26 is extremely small number, right? And yes, so that is the case here. And also note that for the quantum term, equivalence principle, since it's capital M times small m, is obeyed actually. This quantum corrected term coming from the quantum corrections, graviton loops. And for this term, equivalence principle, none of these terms obey any equivalence principle for the non-minimal interactions. And so there we can also distinguish that whether, I mean, at such small order, we can, there is any violation of equivalence principle. If there is, we can conclude that there is non-minimal coupling, and if not, there is no non-minimal coupling. I'll be coming to some other features of this non-minimal coupling when I introduce the light bending in this coupling. So inclusion of spin, I'll be very brief here and only quote the result. Here, I mean, what we are discussing is that I have one scalar which has non-minimal interaction, and I am considering scattering of massive spin half or massive spin 1 particles with that massive scalar object. There will be no non-minimal coupling considered for fermions or the bosons, vector bosons, because, I mean, there is no such physical motivation to do that. So non-minimal coupling will be taken only for the scalar. We'll actually evaluate this similar class of diagrams. Only thing is that this K2 and K2 prime lines will now represent, and these internal lines as well will represent either fermions or bosons, massive bosons. And yes, and for the massive spin 1 field, the Proca field, for the vector boson, we find out this potential. Okay, so you see that the first term, leading term, is once again 1 over r to the power 4. This epsilon and epsilon prime are epsilon of K2 and epsilon of K2 prime. These two are the polarization vectors of the spin 1 field. They represent the creation and annihilation of spin 1 fields at a given vertex, at this K2 K2 prime vertex. So these are the subleading terms. This S is the spin of the field. I'll not go into the detail of how we derive this thing or how these spins and all this stuff are defined. It is unnecessary, but this is the expression. For scalar and spin half scattering, we find this result. Here S is basically the spin, state of this electron. And you see there are diagonal terms as well as off diagonal terms here. S is the matrix element of the spin vector, this vector S, spin operator, which is h bar by 2 sigma I. And yes, here also we find out this leading behavior to be 1 over r to the power 4. And of course, I mean, all of this, I mean, very violently violate the equivalence principle. Well, we have just recently put this work in archive, and let's discuss inclusion of a positive lambda. Process, how much time do I have?
Like 10-15 minutes. It's up to you. I mean,
Okay, I'll finish quickly. Yeah. So let us now consider inclusion of a positive cosmological constant. In principle, this is also valid. The calculation is also valid for negative lambda as well. But I mean, I have a nice motivation if the lambda is positive, and also positive lambda is much more realistic. It's physical, right? So I'll take non-minimal scalar, massive non-minimal scalar, and now my gravitational action contains a cosmological constant term, lambda. So all of us know that in general, I mean, I have a de Sitter background or a variant of de Sitter, in this case, in the presence of cosmological constant. And I mean, in this case, I mean, the standard framework with what I discussed, the standard S-matrix quantum field theory, in-out quantum field theory is never possible. Because, I mean, the vacuum is unstable in de Sitter background. I always have vacuum decay and particle creation issues. That's how usually one cannot do scattering calculations in curved background. However, I mean, there is a point to note here. Let us take a mass or structure sitting in the de Sitter background, and let us calculate the geodesic equation and takes the non-relativistic limit. Let us imagine a massive particle is moving in the radial direction. Its equation of motion is given by this in the non-relativistic limit. d2r dt2 is the radial acceleration, equals gm over r square minus lambda r over 3. Lambda is positive, we have taken. So you see that the right hand side will be vanishing, that is the acceleration will be 0 at some radial point, which is called the maximum turnaround radius, which is given by 3 mg by lambda square root to the power 1, root 1/3. And actually this maximum turnaround radius has a connection to the maximum size of large scale cosmic structures. So the point is that within this maximum turnaround radius, or if we consider processes, quantum processes whose wavelength are small compared to this maximum turnaround radius, or maximum up to this maximum turnaround radius, then I mean this process or these particles associated with this process will not see what is happening beyond the maximum turnaround radius. The beyond maximum turnaround radius is repulsion dominated. It's dominated by the cosmic expansion. And once we are decoupled from this cosmic expansion, we can work in the weak gravity region. So this positive lambda actually, along with the mass of this object of any given structure, actually sets a scale up to which we can treat the background to be flat, and we can do this kind of calculations, scattering calculations, standard scattering calculations. Provided we are dealing with short wavelength processes. We are not dealing with processes whose wavelengths are comparable to the cosmological event horizon. Basically, that's what we do, because universe is curved, even though we do flat space quantum field theory on an accelerator on Earth, because we are dealing with short wavelength processes. We are not dealing with fields which has wavelengths which can feel the curvature, which are large enough to feel the curvature. That's what we are doing. We are restricting ourselves to the maximum turnaround radius regime. So gravitational perturbations, h mu nu, now obeys this equation. And you see that h mu nu has two parts. One is this lambda r square eta mu nu by 3 kappa part. This is a classical part. It gives the classical curvature, background curvature, de Sitter curvature, r equals 4 times lambda. This h mu nu homogeneous part actually will give you the field quantization. Will quantize h mu nu homogeneous, and it will give you the graviton propagator. The lambda part of the action, if I expand, it looks like this. It is an infinite expansion once again. And you see, I have a cubic term here, and that generates a 3 graviton vortex. And so the thing is that we once again, solve for this, evaluate these diagrams with 3 graviton vortices by inserting 3 graviton vortices here. The usual minimal, these are usual minimal 3 graviton vortex. It contains graviton momentum. However, here you can see that this is complementary, because here I do not have any derivative of h mu nu, so I do not have any explicit appearance of the graviton momentum. So if I do this and do the calculations, I find this potential. Okay, this two-body long-range potential. So once again, it violates badly the equivalence principle. The second term I'm talking about, the first term not. And it is extremely tiny in today's universe due to the appearance of this lambda term, but it could be significant in the UV scales physics in the early universe scenario where the lambda value is high. I mean, this correction could be significant. Okay, finally, xi and the bending of light. So once again, we calculate the 2-2 scattering. However, the one field is taken massless. And the thing is that the scalar, I mean, I have imagined this non-minimal massive scalar model, say AV, and non-relativistic mass like a star. The other field is massless, so there is no question of non-relativistic limit here. So, I mean, we assume the bending angle to be small. And for scalar-scalar, massive scalar, massless scalar, we find this bending angle. And for massive scalar and, photon, we find this bending angle. Once again, this epsilon and epsilon star are the polarizations of the photon. They indicate creation and annihilation of the photon in a given vertex. B is the impact parameter. E is the energy of the photon, incoming photon, or frequency of the incoming photon. So the leading result, recall that which can be classically found or found by scattering calculations at the tree level, at the lowest order, is theta equals 4gm over b. However, note that here I have this capital M, mass of this heavy object in the massive object sitting in the denominator. This peculiarity arises, as I mentioned earlier as well, due to the fact that in the non-minimal vertex, there is no appearance explicitly the momentum of the scalar itself. And that's why, in the minimal vertex, I have terms like k1 square, or k1 prime square, or k1 dot k1 prime, or k1 and k1 prime in the momentum of that scalar. And accordingly, I have in the non-relativistic limit the masses of that object. However, here I do not have any such thing. Instead, I have the explicitly the graviton's momentum, and that's why this peculiarity arises. And it shows that, this impossible prediction, it makes these impossible predictions that if I make the mass to be very small, the angle can be very large, which is unacceptable, right? So there is only one solution. If I assume that xi exists, that xi, this parameter, must have some dependence upon this mass m. That is, if I have, this mass to be very small, xi has to be very small as well. And if mass is very large, xi has to be large as well, in order to avoid this unphysical result. Otherwise, we need to accept that this non-minimal coupling does not exist at all in nature. So this is something in this work is in preparation, and we'll put it soon in the archive. So I'll complete with some outlook. Further possible explorations in xi could include, for example, the renormalization group flow of it. For example, the anticipation we just have made that xi has some dependence upon the mass. The investigation of RG flow of xi could help us understand this. What happens to the metric corrections with xi? For example, the correction to the Schwarzschild metric, the Carr metric. Can xi add any qualitatively new feature to soft graviton theorems? The soft graviton theorems are some universal things investigated for the minimal gravity, and they are connected to the asymptotic spacetime symmetry, spacetime's asymptotic symmetry group. So usually taken the spacetime is taken to be asymptotically flat, and the asymptotic symmetry group is taken to be the Poincare group, or the same as that of the Minkowski spacetime. However, if we relax a little bit the fall off of the inverse metric, then it turns out the asymptotic symmetry group is infinite dimensional. It is called the BMS group, Bondi-Meissner-Sachs group. Can this xi, alter these soft graviton theorems and they can qualitatively change the asymptotic symmetry group, this BMS group, when keeping in mind this, peculiar, complementary feature, contrary feature of these non-minimal vertices compared to the minimal ones. Various observables, for example, the two-body potentials, light bending, metric corrections, and general gravitational waves in the effective field theory framework, not necessarily in the non-minimal coupling, for the various alternative gravity theories can be investigated. And what will be the effect of macroscopic spin and finite size of the gravitating effect on light bending? Why not bending of gravitons? What happens there? Also, we can check various alternative gravity theories there. Perhaps I mentioned that I have started this probing these directions, and I hope to come back to these issues, at least some of them, in the future works. So thank you very much for your very kind attention.
Thank you very much, Sourav, for the very nice talk. Are there any questions from the audience? I have a couple actually till
Yes,
someone.
yes, please go ahead.
Well, I mean, in my mind, first of all, yeah, I'm not an expert on quantum field theory quantum corrections in general, but like at least classically, to me, this looks like a scalar tensor theory, where couplings like this psi are bounded very hard by solar system data, right? So how does this quantum potential relate to those classical constraints? Does the screening that you mentioned let this psi escape the solar system tests, or how does this?
So for solar system test, what we need to do is we take this, for example, this potential. Let's take the leading order term, and we can actually take M to be capital M to be Mercury. Sorry, capital M to be the Sun, and little m to be the Mercury, and we actually modify the gravitational potential accordingly. And using that, we can actually calculate perihelion precision, and we can, because perihelion precision's data is much more robust compared to the data of light bending. And there we can actually try to constrain what the xi value is. But I'm not sure whether from classical computations anybody has tried to constrain xi, because then you need to solve for the metric, right? I don't know whether modification of Schwarzschild metric with xi, general xi value with a mass m has been done. Of course, for m equal to 0 and xi equal to 1/6, that is the conformal invariant scalar field, people have calculated this thing and the metric. Yeah. But for for generic xi with a mass m, because if I want to study Mercury's perihelion precision, I cannot take xi to be massless. Sorry, m to be massless, little m.
Yeah.
So
sure.
then, I don't know. Whether people have tried to constrain xi, I don't know.
Yeah, with a massive scalar field.
I'm not sure.
And what about, so I think you mentioned something in the last slide. So is there any regime, for example, that you expect, like early universe, strong gravity, I don't know, anything, that this potential somehow becomes observable?
Not in this form, actually, because I have to work there in de Sitter background. First of all, the potential will not be exactly in this form, but it will have some similarities. For example, this g square lambda will be sitting there. Okay. My point was that since lambda is very small here, so if you take this ratio, g times lambda, okay, then this g time lambda is basically the ratio of Planck length divided by length scale of the cosmological horizon whole square. And since the length scale of the cosmological horizon is very large today, it is suppressed. However, I mean, in the early universe, this lambda density was, dark energy density was rather high, and that's why I believe these corrections could be large actually. Although the method of solving, finding out this potential in this early universe, I mean, this is just an indication about early universe, but in the method of finding the potential in the early universe will not be the same as here, because I mean, in a strict curved background like the primordial de Sitter, uh, we cannot actually do the scattering. There is a problem actually. These are non-equilibrium systems. However, it indicates that there could be some interesting corrections. If I have understood it
Nice.
correctly, of course.
Yeah. Thank you. Any other questions? Okay, let me ask one more. So is there any, so the potential now that you mentioned, for example, the xi equals 1/6, the conformal limit. So is there
Hmm.
any smooth conformal limit, or does this, because you have like 1/1 over m dependence in the potential, right?
No, I do not
So
have any smooth conformal limit here.
yeah,
I don't have.
so it
Look
diverges
at,
basically.
look at this.
Yeah,
Because I mean, the reason is that if you look into this definition of this potential, it is like this. Okay, the mass is sitting in the denominator. Hmm.
yeah,
So I mean, so once I have divided it by the mass, I have already assumed that mass cannot be zero. So that's why we cannot take this little m goes to
yeah.
zero
That's true.
here. And also this problem of vertex is also there.
Mm-hmm.
One thing I just wanted to mention that I mean, one might argue that I can also do these calculations by trying to find out the finding out, trying to by trying to calculate the matrix. The problem is that in the realistic scenario, why these calculations are getting popular, I mean, in the community, this effective field theory framework and all this, because I mean, in the realistic scenario, the gravitating object has, if we move closer, because now we can probe, I mean, strong gravity regime, the deviation from spherical symmetry or axis symmetry becomes more and more prominent. So, in order to know exactly what the potential is, we need to solve the problem without asserting any symmetry as far as practicable, right? So, this framework, this effective field theory and the scattering framework, actually another framework is of course this numerical relativity. Actually gives us this, one opportunity to find out, of course, obviously perturbatively, what is the potential. For example, it gives us an opportunity to find out the two-body potential when the body is moving. Let's say two bodies are moving, they have some relative speed with respect to each other, and that's why they can be very useful. And I mean, in these windows, actually we can check various alternative gravity theories as well, for example the scalar tensor theories.
Mm-hmm. Nice.
uh,
Any?
yeah so
Yeah, there is a question in the chat actually. Let me read it. So, yeah. Intuitively, this correction to the scattering amplitude would also enter the computation of, say, GW emission during an spiral. Do you expect it to break the vanishing lobe number?
I didn't get the question.
So, intuitively, I mean, it's in the chat. It's written in the chat. You can read it as well if you want.
Oh,
Uh, Intuitively, this correction to the scattering amplitude would also enter the computation of GW emission, like during in spiral.
yes.
Do you expect it to break the vanishing Love number?
I have no idea, but I have, as I said, that these are in my radar. I just started these things, this direction, probing these directions, maybe 6 months, 7 months. So, but I have
Hmm.
it radar. I would like to see this, that what happens there. because as I said, the motivation is that the xi r phi square coupling is very necessary if we wish to do quantum field theory or phi-4 theory in curved spacetime. Phi-4 theory in curved spacetime is very much physical if you look into these inflationary backgrounds. So, I mean, we cannot just rule it out. And then we must try to understand that, I mean, whether it actually exists in nature or not. So it will be interesting to look into this. Yeah.
Yeah.
But offhand, I cannot tell about this GW thing. But of course, it will affect. But how much it will affect, or I mean, whether we can constrain it from these GW calculations, that I cannot offhand tell.
Yeah, thank you very much. Yeah, if there are no questions, let me stop the recording here, and then